So we are going to start talking about edge detection. This is lecture 3, and we will cover gradient operators in that Prewitt and Sobel. These are the researchers, these operators named after them. And then we'll talk about Laplacian of Gaussian edge detector. It's a major breakthrough which happened in 1980, and this is also called Marr Hildreth edge detector. Then also gradient of Gaussian, which is called Canny edge detector. So edge detection in simple terms is that we want to come up with automatically from an image, we want to come up with this kind of line drawing. Okay, so this will identify the sudden changes or discontinuities in an image, and these will be the most semantic and shape information we can get from the edges, and it'll be of course more compact because most of the details in the image are, grade levels are constant, but the places where there's a discontinuity or change, those are the places we have edges. Now, even the artist, when draws the line drawing like this, needs to have some high-level knowledge that it's a face, this is a hair, there's eyes, and so on. Now the question is, in computer we don't have that knowledge. We just want to look at the image, look at the numbers, and they are 0 to 55, come up with these edges. Okay, so again, these slides, as I said, these are taken from different professors. This is a slide from David Lowe. We are going to talk about his SIFT. So example is that, given an image like this, these are the edges in this image. This is called edge map, and this another image, these are the edges. Okay, so the application of this is that we can find edges, then we can, from there we can group the edges, we can get what the object is and how we can find it. Suppose if you're looking at for the face, then maybe we can start looking at the eyes and nose, mouth, and so on, and these can be in principle found by edge detection. So edge detection in image is the place or pixels where intensity or color changes. As you see that there's an edge here because there's a white background, and this is a green, and this is an edge here, and this is the edge here, these colors are changing, and so on. So in detail, edges are called by a variety of factors. Again, it's a slide from Professor Steve Sides at University of Washington. So these are the origin of edges. Number one, when there's a surface normal discontinuity. Now if you look at this bottle, then the surface normal, the normal to the surface, in this one it is facing out of the page, and here the orientation or surface normal is little different because it's facing other way. So these are the places where surface orientation has discontinuity, it changes, and these are one source of edges. And here's a depth, the distance from camera to the object. Here the depth is changing because there's some depth because this shape is there, but the depth immediately changes. And this is the surface color discontinuity. As you see, this is a completely dark, and then there's a white. So there's a discontinuity. And then the illumination discontinuity. So this is a shadow of this object like that, and that can be also the edge. So there are many different ways these edges are formed, and so this has been an active area of research. Actually, most of the work in computer vision started from edge detection. So this is 45 years of boundary edge detection, and this shows you how the field has progressed. As you see, starting from 65, we are here in the 2008 or 2014, and the question is that how do you measure if the edge detector is good, if your program is doing well? So one way to measure many of the things in computer vision is what is called precision recall curve. Okay, so here is the recall, and here's a precision, and as you see, the precision recall has changed from the early edge detector to this one, and this is actually the human precision recall, which is shown here in the dot with a green. So let's talk a little bit about what we mean by precision recall. So let's say these are the results of your algorithm. Like edge detector tells you this is set, these are the edges your edge detector found. Okay, and these are actually ground truths. So you give it to human image like that and say, well, identify where are the edges. So human will go one by one and say these are the edges. So this is one set from your edge detector algorithm computer program, and one set is from human. So we want to look at the intersection of those. And so in this we can describe that this intersection is actually true positive, which means these were the edges and the computer program found the edges. Okay, so then these are the true negative, that there were no edges and the computer program did not find, the ground truth did not find. And similarly, these are the false negative, that the computer program did not find but they were actually edges. Okay, and then these are the false positive. I'm sorry, these were the false positive. The computer program found, say there are edges, but actually they were not the edges. So this one is the result of method. So blue one is your computer program tell you that there are edges, and this intersection is fine. And these were, it told you there are edges, but actually they are not edges. So that's called a false positive, because it tells you it's positive, but it's a false. And then these one are which is missed. They say they are false negative. So whenever you look at the performance of a program, you have to compare with human, what the best human can do, and then to describe a metric, and we always talk about precision recall. So precision recall are defined like that we take the ground truth, find the intersection with whatever the algorithm give you, so which is this intersection, divided by what's algorithm found. So that's called precision. And the recall is the same intersection divided by the ground truth. So it is the percentage with respect to how many ground truths were there and what you found, that's called recall. And percentage that how many you found, your algorithm found, compared to what was the ground truth. And that gives you idea of both the false positive, false negative, and all those things. So going back to this thing, this is the way the things have gone, starting from 1965, and the human performance is here. Okay, ultimately, of course, you want 100% precision, 100% recall, that you want completely, very, very good, but it's very difficult. Even humans cannot do it. So which means it's important area to find the edges. Okay, so here's an example of an image. And this is what human found, that these are the edges. And then this is one of the best edge detector will find. Yes?
When we're talking about the ground truth, though, this is human-based.
Yes, right? Yes.
So, but even the humans don't really have 100%
exactly.
precision. So
yes.
It's already kind of...
Exactly. Yeah, that's what exactly I was telling you here. So see, the human for this data set is here. This is a precision recall of humans. So we want to be here. But still we are very far from humans. The best algorithm we have is here.
What I mean then, our calculations of recall and precision are kind of based on our perception, since we're using ground truth in order to calculate it.
Yeah.
But our ground truth is already human bias.
Yeah, no, that's a good point. So see, the idea is that one is that humans are actually asked to look at each edge point, that's count, this is edge point, this is edge point, this is edge point, that's let's say like a ground truth. Now other thing is that human are shown this picture and just say, well, draw a line. The people look at and say, well, this is so that's that's the real performance of humans. Other one is you ask undergraduate students click points and do this. It takes hours and hours. That's the two things. Okay. Yes.
Could you say a little bit more about what does recall mean?
So recall means that this is the intersection between your ground truth, which is shown in the red, all the set points, set of points which were determined by ground truth. We know for sure, it's a truth, that these are the edges. Okay? And the blue one is what the program found. Okay? So we'll apply a program, find the edges, that we know which points are there. So we'll find intersection between those two. Yes? And that is this intersection, and these are the terms. Now when we take this intersection, divide by the blue area, that becomes the precision, divide by the red area, that becomes the recall. Okay? So that's the difference, the precision recall. Yes?
I want to know the false negatives. Because it's part of the ground truth, so it won't be the false. The false negative means it's false and then have no response. So I think it's not belong to the right circle.
No, false negative means that we know that this edge, but the program did not find it. That's called false negative.
True positive.
Huh?
True negative, I think.
I mean, this one is the, yeah, I mean, you can, basically this is saying that it tells you as an edge, it says it's a positive, it did not find it. It wasn't the edge, that's called false positive. And
the program
falsely labeled it, that's an edge, but it wasn't edge. Okay, so that's the difference. Any other question? Okay, so this is another example. This is of a picture. This is what a human draw, and this is what the computer program does, and it's pretty close. And some more example. This is a base edge detector, as you saw at the top one. Okay, so we go a little deeper. So we say what's an edge, as we talk about, and it's a discontinuity in intensity. And there are different kinds of discontinuities. This is the step edge. There's instantaneous change from one level to other. There's a ramp edge, which is a gradual change. This is a roof edge, which is a change and then go down. And this is like a spike, little kind of change and then go down. So let's look at close-up. Again, these are borrowed from other professors. So this is an image, and if you look at this little window, these are that's a profile of intensity. And as you see, these are the edges. These are the changes. There are several of those, There are actually 3 different changes. There are some are gradual, some are more, and these are all the changes which are happening. Okay? Now, if you look at this one, there's one change. If you look at this one, then there are these, another pattern. So there are lots of these things which the computer program has to capture. So edge is a place where there's a rapid change, and so if this is an image, if you look at the profile, just the one row which is shown on red, it looks like that. It was bright, then dark, and then bright. Okay? So now, of course, whenever there's change, you want to find derivative. You want to differentiate. You want to find the rate of change. And this will be a derivative. As you see, there are 2 edges. One is here, other is here. There's a constant between, we don't care. And the derivative of that is 0. Okay? So these are the places where we want to find. And so if you look at this row, which is shown in red, this is a profile of that. And then this can be a derivative of that, and these, wherever there's a change, you get the spikes. So now, as we have been talking about since last week, that there's always a noise in the issue. So if you take that row I showed you before, add some little noise, it will look like that. Okay. Now if you find a derivative of that, this is another example that we have here, that even though earlier it was a step function, but now we have added noise, little noise. Even though for humans it looks very nice edge, but there is a noise. If you find the derivative, it looks like that. It's very noisy, but the derivative is amplifying a noise, and that's a problem. Okay, so we don't know where is the edge. So so noise as effect, and we want to suppress that effect, and we want to look at the pixels, normally have to be similar to neighboring pixel. If the pixel is different from neighboring pixel, except its discontinuity, we need to, consider that fact. And generally, the large noise is stronger response. What can we do about it? So again, the same example. So we have this function, the row from an image, and it has a noise. And so we will smooth it, as we have talked about before. So let's apply a Gaussian filter, smooth with the Gaussian, okay? And then it will look like that. Now its noise is removed, and it's very nice. We can find that. And then what we can do is differentiate it. So if you differentiate this, it will look like that. So, and that's a very nice peak. We say, well, there's an edge there. It's very easy, okay? And that's what we are getting into. So as we have talked about, that the derivative and convolution, they are associative, which means if we take an image and first apply the Gaussian filter and differentiate, or we can take an Gaussian, differentiate it, and then apply it to the image. They are the same. So we can, change this association. And actually, this will be easier because we have a formula for Gaussian. We can differentiate it numerically and then get a mask, apply that filter, as compared to applying Gaussian to image and then differentiating numerically. Okay, and this actually saves operation because here we have this one and then derivative, but here we just have one. The derivative is done analytically. And so this is your f, and this is the derivative of Gaussian. It looks like that in one dimension. Then apply it to that, it looks like that. So this is exactly same as it was done before, but there first we are smoothing, then we are differentiating. Okay, so that's good. That's what we want to do. So that's good. So please, interrupt me if you have any questions. So now we can do the same thing in 2D. So this is a 2D Gaussian. Again, the symmetric, circular symmetric, and all this thing, and we can differentiate it. Apply this mask, and look like that. That is the derivative of Gaussian. And so now there's always a trade-off that how much you want to smooth. If you smooth too much, then you lose in lots of details, and if you smooth little, then you will still have noise. And also, if you smooth too much, then the edge will be displaced. You won't be able to localize the edge at the right place. It will maybe observed at 2 pixels on the right or 1 pixel on the left. So that's a problem. So here is smoothing using 1 pixel, Gaussian 3 pixels, and so on. I'll give you some example. So there's a whole issue of scale. The smoothing in a way is a scale. The Gaussian standard deviation sigma is a scale, and we're going to talk more about the scale. That's a big issue in computer vision, and there are lots of interesting concepts there. But right now scale is the sigma, which is the standard deviation of Gaussian. So going back to, we talked about second lecture on the filtering, that we want to differentiate a function. And this is the definition of a different derivative of function in one dimension you learn in calculus. You take a value of function at x plus eta small, and then f of x, and find the difference, divide by this small distance, and you take this so small that it tends to 0, and that is the derivative. So we need to fix this one. Wakas, can you note this? This should be, I think we should make this delta x also. So so that's, you learn this one. That's what we are going to do. And we talked about that, well, we are doing with the discrete images because they are not continuous. So delta x or delta e can be small as possibly 1. Otherwise it will be 0 because we have integer 1, 2, 3, 4 and things like that. So therefore then this reduces to pretty simple finite difference, that you take the value of pixel here and then go to the back and subtract, or go to the forward and subtract. So that's why we have this backward difference, forward difference, center difference we talked about, on Thursday. This is just a review. So derivative in Gaussian in a 2-dimension, again we have the similar idea here, but since it's a function of 2-dimension, we can differentiate with respect to x, or we can differentiate with respect to y, and we can apply again approximation, and then we have these masks we have talked about. Okay, so given an image like this, we can find the first derivative with respect to x. It will look like that. This first derivative with respect to y, it looks like that, and this is simple difference operator. So now, as we said, that while the strongly affected by noise, and so the pixels that look very different from their neighbors, and we want to address that. Larger the noise is, the stronger the response, and what needs to be done, that we have to rely the information from the neighbors, so that we don't just rely on the pixel we are looking at, but we rely on the neighbors. That's why we are going to average, or we are going to do weighted average. If you do weighted average, it's like applying Gaussian filter. Okay, so because the noise is a random, it randomly affects some pixel. So hopefully the other surrounding pixel will not be affected, so we can rely on that. If all the pixels are affected, or many pixels are affected, then it's not a really noise. Noise by definition means random. We cannot predict which will be affected. Okay, so that is what we are going to do. So we are going to rely on the smoothing, and that's we already covered that. So this give you an examples of image, and if you keep increasing noise, these images will look more distorted, more blurred, and so on. So so we are going to smooth the image, and that will help us. And as I said, that noise is independent, so it cannot be dependent on other pixels. So suppose here is the image with noise, and we can smooth it. The Gaussian looks better than this, and the Gaussian filter we talked about looks like that: e to the power minus x square plus y square upon 2 sigma square. So sigma is the scale of the Gaussian, and as we talked about before, that we increase the sigma, then it will incorporate more neighborhood. For sigma is equal to 1, then we say 7 by 7 mask is enough. For sigma is equal to 2, will be 13 by 13, because we want 3 sigma on this side, 3 sigma on the other side. That's the idea. Okay, so now let's get into actual edge detector. So we are going to talk about 2 edge detectors, Prewitt and Sobel. These were the researchers who came up with these a long time ago, 65 or 68. And then we'll talk about Laplacian of Gaussian, which is a modern edge detector, and the gradient of Gaussian. Okay, so the Prewitt and Sobel edge detector are very simple. So the idea is that we'll compute derivatives in x and y directions, and they'll give us a gradient vector, and we'll compute the gradient magnitude and gradient direction. Actually, gradient direction will not be used here, so we'll just look at the gradient magnitude. And we'll threshold the gradient magnitude, because gradient magnitude tells you how much is a change, and if you say if change is significant, then that's edge, otherwise it's not edge. That's it. That's a very simple idea. So so the process is that we take an image, we smooth the image, we'll get a blurred images or smooth images, and then we find derivative in x direction, and that kind of give you edges in x. So for smoothing, we will do kind of equal averaging, so 3 by 3 neighborhood, 3 pixels, and for the derivative we are going to use this the central difference. So it's like that. Now these are kind of separable things, So first you smoothing, then find derivative. And if you multiply these two, so there's 3 by 1 and 1 by 3, then you will get 3 by 3 matrix. And that will be like that. So see, the idea is multiply 1, here you will get this column, 0, you'll get 0 column, minus 1, you'll get this, and that is the Prewitt edge detector in the X direction. So it has the average, equal weight to all 3 pixels or 3 by 3 neighborhood and then difference. And we can do the same thing for the Y, and here again we will do the filtering and then we'll do the difference. So the filtering will be 1 0 minus 1 as we had before, and then this is your 1 1 1, and again you can multiply these two, you will get the mask like that. So that is the separation of this in two one-dimensional mask. Okay, so Sobel is exactly same. The only difference is that instead of equal weighted, we will have different weight for the central pixel. So here we will have 1 2 1. Remember there we have 1 1 1. Everybody's weighted equally. Central pixel weighted twice as much, and the same thing, the derivative, and then you get this mask, and this one in the Y direction you get this mask. So that is nice. So you know now that we are smoothing. In the Prewitt we are equally weighted smoothing. In this one this is weighted smoothing, and then finding the central difference, and we are separable. Okay, yeah.
In the second one, it doesn't edge in Y, right?
Yeah. The first one is X, and yeah.
Why is the order different?
Yeah, I just try to put, so see, you want to visualize that you can take these and get a 3 by 3 matrix,
Okay.
So what's going to happen here, that you're going to multiply with 1, you'll get this, multiply with 2, you'll get second column, multiply with this, you'll get a third column.
But conceptually, we always smooth first, and then we take...
Yeah, whichever way you want to do it.
Oh, it's...
Yeah, ultimately, you want to, do like this. So this tells you...
In the second line, the derivative is not a consequence of blur.
Huh?
The second line, the Y direction, the derivative is not resulting in blur.
Yeah, so this we need to change that way. So it should be smooth. Okay, note down please. That's good. Okay. Huh?
The one below should be adjacent Y.
Yeah, this also should be adjacent Y. Very good. Okay, so you're making progress. Yeah, go ahead. You had a question? Yeah.
So at the end we have a matrix, and that will give us all the values for the points around the point. Do we add them up on average?
Yeah, so we're going to talk about that. So see, what this will give you fx, the first derivative in x direction, and first derivative in y direction, and then there will become vector. Okay, so this is the gradient, and we'll find the magnitude of that. So the vector has a two component, this one, comma, that one. For each pixel we have two numbers. The first derivative is x, first derivative is y. So the vector, so we'll find a magnitude of that. Square, and then sum them up, then under root. So we are going to use a magnitude to find the edges. So those will give you edges in any directions. Yes?
That step would be the same for Prewitt as well, only that we would
Yeah,
mask.
exactly same. Yes, it'll be same in all. Because see, this is a basic definition that you have a function, you find the gradient of that function. So this is a 2 dimension, so you will have, this function is of 2 dimension, f, x, y. Now you differentiate this, so you will differentiate with respect to x, differentiate with respect to y. It's called fx, fy, it's a vector. Now this vector, you can find the magnitude, you can find the direction. So right now in the Sobel and Prewitt, we are going to use only magnitude. It will tell you how much is the change, and then apply a threshold on that, okay, which is here. So this is a derivative in x direction, derivative in y direction, and this one is the magnitude at the top, and we apply a threshold. If it is more than 100, these are the edges. So that's what you get. Very nice. So you learn calculus to do derivative. Now you can see the visually. So this is what derivative is doing. Okay. So now, this was kind of toy thing, long time ago, because it was always the science is harder in the beginning, but then it becomes, if you look at now, the old problems are easier because we have gone through generations, and now this generation is supposed to solve harder problems. So now the next level of edge detection started in 1980, and this is called Marr Hildreth edge detector. There were two researchers, David Marr. So David Marr is one of the most famous computer vision researcher. And in this picture, here is David Marr. Here is the Tommy Poggio. He was a postdoc with David Marr at MIT. And here is the Francis Crick. He was the guy did the, I think, DNA and was a researcher in,
Wilson and Crick, right?
Yeah, that guy. So now David Marr was a neurophysiologist. He was English from England, and he studied a lot about how the human brain and Kate's brain and work and all those things. And so he came as a visitor to MIT and got interested in computer vision, and then he started this lots of interesting work. There are many PhDs under David Marr from MIT. He actually changed the direction of computer vision research, and he actually wrote this book, very influential book called Vision, and I strongly recommend that you read that. It's very easy, scientific, American level, reading. It's not very technical. So the sad thing was that he had got a cancer. He passed away very quickly. He was actually lost. He died before doing the last edits, and actually there's a whole chapter about conversation with Tommy Poggio and David Marr. He's asking questions and he's replying. So as a tribute to David Marr, there's a most prestigious award in computer vision. It's called Marr Prize. So if you go on the web, you'll say Marr Prize, and people get that. As every ICCV, International Conference of Computer Vision, that prize is given. And Ellen Hildreth was his last master's student. She actually wanted to do PhD, but the guy passed away before doing PhD. So she did a master thesis on this edge detector, and there was this background work, at Harvard University. These were two scientists, Hubel and Wiesel. They got Nobel Prize in 1981, also discovering these different cells in the retina of Kate and so on. And this was all inspired from that work. And so the idea, they published this paper called Theory of Edge Detection in the Philosophical Transactions, Royal Society of London. And so let's talk about what Marr Hildreth edge detector does. So again, it will do smoothing by Gaussian, which you know by now pretty well. And instead of finding the gradient of Gaussian, it will find the Laplacian. Instead of the first derivative, find Laplacian. Laplacian is the second derivative x plus second derivative y. Okay? And this Laplacian is very used a lot in lots of different things, quantum mechanics and electromagnetics and so on. And then instead of finding the maxima in the gradient magnitude, we'll find the zero crossing in the Laplacian. So you have learned from calculus, if the function is maxima or minima in the first derivative, then second derivative has to be 0. Okay? That's the way you do that. And so since we are finding a second derivative here, so we look at a 0 or zero crossing as compared to maxima in the first derivative. And the motivation was that it is better, it's easier to find 0 than find the maximum minimum, because you have to have a threshold, which threshold. So that was the thing. So we'll apply Gaussian, find the Laplacian, then we will scan the image, find the 0 crossings along each row and along each column, and these will be the edges. So Laplacian is from this famous French mathematician, Pierre-Simon Laplace, and he was born in 1749, 23rd March, and died in Paris, 1827, and he was a mathematician, astronomer, and he did lots of things. So this is from Wikipedia, and he was not a modest person, but he did lots of good contributions. So it's good to look at history of science. Look at these guys, how much they did, and we are still talking about these, after 200 years. So now let's get back to Marr Hildreth detector. So we are doing smoothing by Gaussian, and so we take an image and we do the Gaussian smoothing, get a smooth image, and then this is the Gaussian filter, and then it looks like that, and then we find the second derivative with respect to x plus second derivative with respect to y, and that becomes Laplacian. Okay, so now you want to be careful that these symbols, if you have this triangle upside down, it's called gradient, but if it is up, this is upside up, this one, then it is Laplacian with a square. So this is inverted, this is straight but squared. So these are the symbols mathematicians have used, and we are going to use those, so don't get confused. Okay, so now how do we derive the Laplacian of Gaussian? We can just come up with a mask for this, and so we have here we have an image and we are convolving with Gaussian, then we get a result and we are finding Laplacian of that. Okay, now as we said, these are associative, so we can find the Laplacian of Gaussian first, then apply it to the image. These are equivalent, and this will be easier because we already know the Gaussian. We can differentiate with respect to x, then differentiate again with respect to x, then differentiate with respect to y, differentiate again with respect to y, add it up, that becomes Laplacian of Gaussian. So let's say you want to differentiate this with respect to x. So this is exponential, so which means that will be same thing, then we'll differentiate this with respect to x, will become minus 2x upon this. So that is the first derivative of Gaussian with respect to x, like that. And you can then differentiate again with respect to x, and then differentiate this with respect to y, and again you add that up, you will get something like that. So that is called Laplacian Gaussian, and you should do that at home, and I think this may be a homework also. It's just practice for you to remember what how the differentiation worked, what you did before in the calculus class, because the different derivative of the exponential is exponential, but then you have to differentiate whatever the exponent is with respect to that, and so on. Okay, so it looks like that. If you plot it, it looks like that, and it's like a Mexican hat. This is called a Mexican hat edge detector filter. Okay, so inverted Mexican hat. It's not Mexican hat is other way, but it's inverted. So Gaussian is this, and we have talked about this, that this is a parameter standard deviation sigma, and you can generate this mask by taking different values of x, plug in this, and if you put x is equal 0, this will become 1. Put x is equal 1, it will become 0.6. It's equal to 2, it will become 0.13, and so on. Now, since this is symmetric, so x is minus 1 will be exactly same. Minus 2 will be exactly same like this, and so on. So it looks like that in one dimension. And the 2D Gaussian is like that. So again, you can take different values of x and y. So your center x is 0, y is 0, so it will become 1, and I just have multiplied by 255 to make all integer. Then as you see, that's very high at the center, then it's going down. So you can also generate that yourself to feel comfortable. And here I've taken sigma is equal to 2. So that's why this is 13 by 13 mask. Looks like that. And so, so the Laplacian of Gaussian filter is this, and then you can take the same thing, take different values of x and y, and then you will get these kind of values. So as you see, then center is negative and then outside positive and so on. And you can verify that. That looks like that. Because here, you take different values of x and y. This one, say x is 0, 0, x is 0, y is 0, x is 1, y is 0, and like that. You can take different values and populate this. And don't worry about this constant here. So now once we know how to generate a filter and apply to the image, then we will find the zero crossings to find the edges. So as I said, it's a major difference in finding the maxima in the magnitude of gradient. Here we are finding zero crossing in the Laplacian. So now when you scan the image, then there are 4 different kinds of zero crossings can happen in the image. One is the pixel is positive and the next pixel is negative. That's a zero crossing, because positive, negative, somewhere it has to be 0. Okay? Because a discrete image, so we don't have exactly where it became 0, but it's obvious positive, negative. Or it can be positive, 0, negative. It's a clear 0, so that's a zero crossing. Or it can be negative, positive. Also it's a zero crossing. So one is going from low to high, other is going from low to high, from high to low. Okay, so same way, negative, positive, negative, 0, and positive. So now, even though when this edge detector came to be known, the big thing was that, well, you don't need a threshold. Just look at zero crossings, obvious compared to the other edge detector where you apply threshold, Sobel and Prewitt and so on. But in a way, you will find out that you do have to apply some threshold, because zero crossings can be some very weak zero crossings, and that will give you weak edges. So therefore, you have to find the slope of zero crossing. So when something goes from A to minus B, the slope is A plus B, the change, from A to minus B. And that you can kind of apply threshold on that. Compute the slope of zero crossing, apply threshold to slope. So now, as we have been talking about, that the Gaussian is separable filter, okay, which means we can do this, in 2 one-dimensional filters. Of course, if you don't want, if you do just 2 dimension, then you will have n square multiplication per pixel. But since it's separable, that we can do one-dimensional convolution x direction, get the result, and then do one-dimensional in y direction, and that will have the better computation, only 2n compared to n squared. So, and these are the masks as we have been seeing. You apply the same mask, first is row, get the result, apply columns, and you're done. Okay? So now the question is that, can we do this? Is Laplacian and Gaussian separable? No. So it is not separable in a way just you can do in two one-dimensional convolution, but it is separable that you can do in 4 one-dimensional convolution instead of 2 one-dimensional. It still is good because the 4n is still less than n squared. Okay, so that's what we have here. So this is of course, this is associative, as we said. You can apply the Gaussian filter first, find the Laplacian, or take the Gaussian, find the Laplacian, and then do that. And these kind of things we can do. So requires n square multiplication, and but we can do this in 4 one-dimensional convolution, which will be better. So what we are going to do, we'll take an image, apply the second derivative of Gaussian marks around x direction on each row, get the result, then apply the only Gaussian mask along each column. So we get one term. We repeat that thing, we apply the second derivative Gaussian mask in one dimension along each column, get the result, apply along each row. We add it up, and it's exactly same as we are going to do here, and you can show that it's shown in my book. You can look at that. And but here we have n square multiplication because our mask is 2D, and here we have each mask is 1D. So for each one we have n multiplication. So 1 here, 2, 3, 4. So that is the advantage of doing that. So if somebody asks you, is Laplacian Gaussian separable? You say, well, it's not really separable in 2 1D convolution, but it's separable 4 1D convolution, and that's a way to do it. Okay. So Gaussian filter is separable. You take an image, apply Gaussian in x direction, get the result, then apply it to y direction. That's a Gaussian. Laplacian Gaussian filter is separable in 4. You take the second derivative Gaussian, apply in x, then apply another just Gaussian in y, and then apply Gaussian, second derivative Gaussian y, then apply just Gaussian x and add it up. And that's the same as Laplacian Gaussian. Okay, so that's good. So if you do all that, this is an image, and this is the output of the convolution. Now as you see, some are negative, some are positive, and then these are the zero crossing. These are the edges, and we are showing all of the zero crossings. So and so in this one also we have to ask a question: what sigma value we should choose? Sigma is 1, 2, 3, 6, and that's called a scale or sigma value, and that also relates to size of the window mask or filter size. And we are showing the edges at different sigma value. If you have small, you'll get lots of edges. If you are large, you get small number of edges, but they'll be more blurry, and these small edges will group together and make the big edge. And we'll discuss this before and after this lecture also. So then the Laplacian of Gaussian algorithm is that either you can use the 2D filter, just take the Laplacian Gaussian filter, apply that, or use 4 1D filters as I just explained to you. Find the zero crossing from each row, find the slope of zero crossings, and apply a threshold to the slopes and mark the edges. So these are the steps in Laplacian and Gaussian. So again, you can see that there's always filtering, there's a differentiation, and there's at the end detection. So these are the 3 kind of steps in the edge detector. In the Prewitt and Sobel, the Prewitt smoothing was simple averaging. Sobel smoothing was the weighted average. The central one is twice as much than the other two. In Laplacian Gaussian, filtering is Gaussian. That's a big jump. That results are better as compared to the simple averaging or the averaging by Sobel. And then other major difference was that instead of finding the gradient and magnitude of gradient, then here you find the Laplacian of the image and find the zero crossing instead of maximum in the gradient magnitude. So that is the difference. Now that leads us to the last edge detector, which is the Canny edge detector. Okay, so around I think the same time when Marr Hildreth edge detector came up, Hildreth was doing master thesis with Marr. There was another student, master students, John Canny, who actually was originally from I think Australia, were doing master thesis with another British scientist, researcher, Brady, Professor Brady, and now he took a very different approach. As you saw, that Marr Hildreth edge detector was motivated by the neurophysiology, because Marr was neurophysiologist, and there was these results from Hubel and Wiesel and so on. And still now, Tommy Pojo was, I think, postdoc, a visitor with Marr. He's still professor at MIT, and he's in brain sciences, and they're continuing how the human brain works and vision works and so on. But this Canny had a different approach, which was pure mathematical, and at the end the result is very similar. The Canny edge detector, in a nutshell, is the gradient of Gaussian as compared to Laplacian Gaussian, Marr Hildreth, but he came up through a different way. So the idea was that we want to look at the quality of an edge. So first is we want to, as we've been talking about, the edge detector edges should be robust to noise. If there's noise, we should be able to deal with that. Second is that edges should be localized properly. Where there's an edge, we should find the edge exactly at that location, not one pixel on the left or right, because these edges delocalize. Sometime you will get too many responses. If there's only one edge, you may get thick edges. You get a couple of pixels at edges. So we want to avoid that. Ideal criteria you want to look at in the edge detector, and that's what this John Canny started. So John Canny actually is our professor at Berkeley. He's not doing vision. He's in robotics. So let's say we have an edge. This is a true edge. These are the pixels, red pixels, which are identified, and then if the edge detector is not robust to noise, then you may get edge response like that. Some of these are correct. You get a wrong edge delocalized here. This is not good. Also, you may get localization that these are shifted, and these may be due to noise and so on. And now this is the thick edges. Instead of 1 pixel as edge, we'll have 3 pixels as edge, and so on. So that's not. So all these things are not good. So you want to fix that. And this is a picture of John Canny, and so he wrote also master thesis. And so you look at, say, let's look at criteria which we want to optimize. You want to come up with an edge detector or a filter which optimize these criteria. So one is it should have good detection, which means it should minimize the probability of false positive as well as false negative. Should not say, this is the edge, but it's not an edge, and we should not miss the edge. That's the problem. Second thing is that it should localize that edges should be detected exactly at the same place where there's a true edge. It should not be 1 pixel on the left or 2 pixels on the right. And then there should be a single response to the, there must be one edge for each point. Okay, so so you went through, and you can look at this thesis, defining these criteria in a function, and then there's a whole optimization step. He automatically came up with the optimal filter, and that simplifies to the gradient of Gaussian, which was very interesting thing. So this is more mathematical, and other was motivated by the neurophysiology. So then steps in Canny detector are smooth image with Gaussian filter, very similar to the Laplacian Gaussian. Compute the derivative of the filter image. Find the magnitude and orientation of gradient. Now this is one major difference also, that so far in edge detectors, Prewitt, Sobel, and Laplacian Gaussian, we have not used a direction information. Because Prewitt and Sobel, we are looking at the magnitude. In the Laplacian Gaussian, there's no direction. It's isotropic. It will give a response, same response if the edge is rotated, in any direction. So this was the first time that in a way the direction was used in Canny detector, and we're going to talk about it, and it makes a big difference. Okay, so another difference was that you apply non-maxima suppressions, and that also made a difference. And another difference was that there was no single threshold, there were two thresholds, low and high, and that's called hysteresis threshold. And so smoothing is Gaussian, derivative is gradient, and that you know pretty well. And so we will get each pixel, we'll get a vector, which is be the derivative in x direction, derivative in y direction. So it's very similar to Prewitt and Sobel. Only difference is that here we are doing Gaussian filtering. There we did average filtering, or simple modification of average filtering in the Sobel. But then it depends on how we use this. So this Gaussian filter, again, this is the mask for first derivative Gaussian with respect to x, mask with respect to y, and if you apply image, this will become x, this will become y derivative, and then we are going to find the magnitude and direction. Magnitude we have already talking about. So direction is a tangent inverse of fy upon fx. We can find direction. So which direction is an edge? Okay. So if it is an image, then this is the gradient magnitude. So if this is the example image, Lena image, and then these are the derivative Gaussian filters, and if you plot them, they look like that, or if you just display as an image, it looks like that. Then you can find these derivative, apply those maths to the Lena image. This is x derivative, this y derivative, the gradient magnitude. Okay, it's more examples. And these are the directions, and there's some color convention we are using the directions. So now let's talk about the, yes?
What do you mean by direction of an edge?
Yeah, so see the let me look at here. So let's say, this is the like object here. So as you see, there's an edge, there's an edge, there's an edge, there's an edge, and there's a rectangle. Now, when you find the gradient, so at this pixel, gradient is a vector. It will always have a direction and the magnitude. Okay, so direction of a gradient is perpendicular to the edge. This is a direction of an edge, and this is the direction of gradient. So edge at that local neighborhood has a direction. Here, there, there. So that's what reflected in the direction of edge. Yes? Okay. So let's talk about the non-maxima suppression. So what this does, that we just don't want to apply a threshold, say, well, if that gradient magnitude is above some threshold, that's an edge, otherwise not. We want to look at that if that gradient magnitude at that local neighborhood is the maximum compared to its neighbors, we will say that's an edge. If it is not, then we will suppress it. So if it is not a maximum in the local neighborhood, then it's a non-maxima, and we are going to suppress it. Now the question is how we are going to look at it. It should be maximum in some direction, and that's where we are going to use the direction of the edge are perpendicular to the gradient direction. Okay, so let's say this is an image, and so we look at direction perpendicular to the edge, which is here, and so as it's shown here, so we want to decide, should we maintain this pixel or we suppress it. So we are going to compare the gradient at this pixel with this and with this, and so if the gradient magnitude, if that xy is greater than x prime y prime and it's greater than x double prime y prime, so it is maximum in the direction perpendicular to the edge, then we say this is a maximum. Okay, because when you find a derivative, the maximum change will happen in the direction of gradient. Okay, so if it is maximum, then we maintain, otherwise make it 0. Now if you look at the change in this direction, there's no change, there's 0 change actually, because they're all constant. Yes, it's all constant. The change is in this way or this way or this way. So that's called non-maxima suppression. We go through each pixel, we know the now direction of edge, we look at in that, compare and do this operation. So that makes a difference, and that's very important. And I think this was not from Canny, this was from Rosenfeld, but he used it very well. So that's good thing. Then what we have, this is a gradient magnitude, and we can apply a threshold. We get edges like this. So threshold greater than 25, these are the edges. There are lots of noisy edges. Now, so we want to do better. So we don't want to apply one threshold, we want to apply 2 thresholds. And the idea is following. So let's first go through the figure, and then we come back to this. So let's say, image has these kind of edges, okay? And let's assume that this is the gradient magnitude and these are the edges. So if we pick the high threshold, then we will have only this part of edge and this part. All these will be removed because there the gradient magnitude is lower than high threshold. Yes, the way we have plotted, and this whole thing will be removed, which is not good because it happens to be this is kind of noisy, but this is, we want the whole thing. Now if you apply low threshold, then all of them will be selected, and this will be selected, which is not good. We don't want that because it's noisy. So therefore what we are going to do, we are going to do low threshold and high threshold. Okay, So we are going to say, well, if there is a edge point which is above high threshold, like this one, we will look at its neighbors, this one, this one, this one. All of those, if they are above low threshold, we are going to select those. And suppose this is also high threshold, but then we pick that and we are going to select. So this whole thing we selected. So if there's only single point which is above high threshold on that contour, and all other points are above low threshold, we'll select the whole thing and get nice contour. But this will not be selected because there's none above high threshold, so we'll get rid of that. So that's called hysteresis threshold, how we use high and low threshold. And that's what is explained here, that says if the gradient at a pixel is above high, declare it as an edge pixel. Below low, declare it as a non-edge pixel. Now if it's between low and high, we consider neighborhood iteratively, and if it has edge pixel which is connected on the edge which is above high, and above high and low, then we say that's if it is connected to the pixel which is above high, of course above high there will be above low also. If it's connected to the pixel which is above high, even though that pixel is not above high, we will select that. Okay? So now the question is, how do we know which pixel is connected? So there's a whole notion of connectedness. So if I'm looking at the pixel here, then the 4 pixels left, right, and top, bottom are connected. This is called 4 connectedness. And this is called 8 connectedness, which is all 8 pixels connected. And this is called 6 connectedness, and so on. Okay, so that's we went through, and so therefore scan the image from left to right. Gradient magnitude of a pixel is above high, declare that an edge point. Then recursively we are going to look at its neighbors. If the gradient magnitude is above low, we declare as an edge point, and that's what you're going to get. This is the regular 1 threshold, and this is the high is 35, low is 15, so it's better than the one on the top. And these are some examples. This is before non-maximum suppression. This is after non-maximum suppression. This is the hysteresis thresholding, and final Canny edges are like that. So it's much better than these. And again, there is issue of what the sigma is. And so I think it's getting late, so I'll finish these couple of things you want to stay here? Can you stay 5 more minutes? Let me finish this. Okay, so let's look at MATLAB functions. So MATLAB has this function called edge, and that supports 6 different edge finding methods: Sobel, Prewitt, Canny, Roberts, Laplacian Gaussian, zero crossing. So suppose if you say edge, image, Laplacian Gaussian for short is LOG, apply a threshold, and what's a sigma, then it will apply Laplacian Gaussian filter to the image. Okay? And it'll store the result in BW1 image. It will ignore all the edges weaker than threshold, and sigma specify the standard deviation that we're talking about. And now if we use the same function, put a Canny here, then it will apply Canny edge detector. And again, sigma is for Gaussian. Now threshold is a vector, which is the high and low threshold. Here the threshold is just one number. And sigma is again the standard deviation of Gaussian. Then image gradient, just find the gradient of an image. and you can specify which method you want, Prewitt, Robert, central difference, and so that's it. So you can look at the chapter 2 from my book and also Rick Zaleski's section 4.2.